The topic here to look and see if the function is continuous at a point. And if you have the graph, you can tell if the function is continuous at a point or not. So let's say we have this graph, x equals to 1. I mean, that's x equals 1 here. And the graph looks like this. And the question, is the function continuous at 1? And if not, what was the reason? Is f of x continuous at x equals to 1? Again, when you have the graph, you can look at it and go, no, the answer is no. I can see a big hole in it. But there are three conditions must exist for the function to be continuous at a point, any point. The first one, the function at the point, we'll call the point C. F of C must be defined. So the function must have a value at that point. So let's look at that. Do we have a value at that point? Do we have a value at 1?
Yes.
And what's the answer? 1. So that test actually passed. Condition number 2. The limit of f of x as x approaches c must exist. That's condition number 2. Do we have a limit? So let's look at this one. What's the limit of f of x as x approaches 1? Well, I'm just saying as x approaches 1. Does not exist. D and E. Why? Because from the left side, what's the answer? 2. From the right side, what's the answer? 1. So there is no limit. So what fails is this test. Once one of these tests fails, the limit does not exist. So this is not continuous. And what was the other condition, the third one? To be continuous, the two answers for 1 and 2 must be the same. So f of c, bless you, must equal the limit of the function as x approaches c. So these are the three conditions that you need to have for a function to be continuous. This must be yes, this must be yes, bless you, this must be yes. If one of them is no, stop right there, it's not continuous. Let me try another picture. And again, when you have the picture, you can look at it, go yes, no, boom, quickly. This is the 2 here. And the question is the function f of x continuous at x equals 2? Question mark. Is it continuous? Well, let's take a look at the three conditions. The first condition, is the function defined? Do we have a value of the function at 2? What is it? It's 1, that big dot right there. See that dot there? This is when x is 2, the y value is 1. So that passes the test. First test. The limit is the limit of f of x as x approaches the 2. Does that exist? What's the limit from the left side? 2. What's the limit from the right side? 2. So there is a limit, which is 2. Condition number 2 passes the test. 2 out of 3 so far.
Not
2 out of 3 ain't bad, as Meatloaf said, you know? Condition number 3. Take the limit of f of x as x approaches 2. Does that equal to, question mark, f of 2? If the answer is yes, the function is continuous. What's your limit? 2. What's the value of the function? 1. Are they equal? No, this test failed. So is the function continuous? No. It's continuous at every point before, every point after, but not at that point. Now again, if you don't have a picture, then we got to look at it. Mathematically, let's take some of them. F of x equals x squared minus 1 divided by what? X minus 1. And if you're going to have any point of discontinuity, where is it going to be? At the bottom. What makes the bottom 0, right? So the question becomes, is f of x continuous? Where? At x equals to 1. And again, I don't want to graph it. If you graph it in your calculator, it's going to show continuous. Watch this. Here's my calculator. Quit. Wait, let me delete this. I don't know how to clear the whole thing. Be ready for next time if I ever need it. Here's my function. I'm going to graph, clear that. If I type in that function, it's going to show me it's continuous, and that would be the wrong answer. Divided by x minus 1. And I go graph it. Do you see any holes in that function?
Well, it's because the factors it out automatically. Gives you x plus 1.
Correct. Because what the calculator does is simplifies that function. So let me factor and simplify. Well, if you factor the top, you're going to have what? X minus 1 times x plus 1 divided by x minus 1. So what the calculator does, here's the calculator. It factors that as x minus 1 times x plus 1 divided by x minus 1, and when you simplify it, what's going to happen? It's going to graph x plus 1, and x plus 1 has no holes in its straight line. So it shows as the function continuous. These two are not exactly the same. Very close. They're different at one point. The point they're different at when x equals to 1. When x equals to 1, this has a value of 2. When x equals to 1, this has a value of what? Undefined. So when I look to see if the function is continuous, I go, well, let's do test number 1. Let's find the value at x equals to 1. I can't. This does not exist. Stop right there. Test number 1 failed. The function is not continuous at 1. Has a hole at 1. We call that removable discontinuity. Why is it removable? Because when you factor that out and you graph this one, it's gone. So you'll hear once in a while removable discontinuity. That's a problem like this, where when you factor it, these two will cancel and it's no longer there, and then you just graph this one, looks like continuous function. What about this one? Now again, this is a straight line, and this is e to the x. By itself, this is continuous. By itself, this is continuous. If you're going to have any hole, it's going to be at 0. Where the two, do they touch each other? Do they meet? Do they fill in all the spots and continue with it? Because I think, but I'm not sure yet, we'll look at it, x plus 1, it's rising, has a y-intercept of 1. It looks like this. And what's e to the x looks like? I think it looks like this. Exponential function. The only question is, does e to the x start from that point, or does it start higher, does it start lower, and there's a gap? I'm not sure. So this by itself is continuous, this by itself is continuous. My question is right around the 0, right there. Do we have a hole or not?
No, you don't.
So again, let's look at the 3 condition. Condition number 1. What is h? We're using h instead of f. What's h of 0? Is the function defined at 0? Do we have a value at 0? At 0, when you got to use that one. It says for x is less than or equal to 0. I got to use the top one. Let x be 0. What's 0 plus 1? 1. So the function is defined as 0.
It's also 1.
Let's look at the limit. But I got to look at the left side and the right side. From the left side, which one I got to use? That's x less than 0. From the left side, I got to use this one. Try direct substitution first. What's 0 plus 1? 1. What is it from the right? I got to use that one. Plug in 0, direct substitution. What's e to the 0? 1. Are these two answers the same? So that means the limit of h of x as x approaches 0 is equal to 1. We have an answer to step number 2. So we got an answer to step 1. We got an answer to step 2. What's step number 3? Are the two answers equal to each other? Is the limit of h of x as x approaches 0, does it equal to h of 0? Well, the answer to this is 1. The answer to this is 1. The answer is yes. So h of x is continuous at 0. Notice the topic of this video is continuity at one point, which we just finished talking about, and an open interval limit. What does that mean? Let's try this problem. Let's say we have this picture. This is x equals to 1. Let's say that's 3. X equals to 4 here. That's a 1. The graph ends right there. See the closed circle? That means ends right there. Now, if I ask you for the limit, we'll call this f of x. As x approaches 1, I can't ask that question. That will not be a correct question. Why? For the limit as x approaches 1, the left side has to match the right side, right? From the left and the right. There is no limit from the left. As you're approaching the 1 from this end, there is no y value. This is known as a one-sided limit. You only have the limit from one side. In this case, you're approaching the 1 from the right side. You can't approach from the left side. The function is not defined. From the right side, as you come from here, what is the y value getting closer to? 3. I can't ask you from the left side. Left side doesn't exist. The function is not defined there. And when you approach the 4, I can only ask you which side? From the left side. As you approach the 4 from this end, what's the y value? 1. But I can't ask you from that end. Function is not defined. And I want to look at this from negative. I don't even have to write this. If you try to graph this, anyone knows what the graph this looks like?
It's kind of like a half circle.
Yes. It's a half circle. Why? If you call f of x y, and to cancel a square root, what do you need? Square both sides, right? So if you square this side, you got to square that side. So you'll have y squared equals 1 minus x squared. Move the x squared to this side, becomes positive. And that's the equation of a circle with radius equals to what? Equals 1. The only problem with that, that's a circle. This is not a circle. This is only the top half of the circle because the bottom half y is negative. Notice it says f of x is positive, the square root. So what you're looking at is a picture that looks like this. Half a circle, the top portion of it, if it had a minus sign in the bottom here, on the front here, a minus sign, it would be the bottom half of the circle. If I was graphing this, that would be a full circle, and that's not a function because of the vertical line test. So to make sure that's really a function, we do only the top half or the bottom half. In this case, we chose the top half because of the plus in front of the square root. If it was a minus, we're looking at the bottom half. And again, this problem, you can only ask for the limit from one side. I can ask you what's the limit of f of x as x approaches what? The negative 1 from which side? From the left or the right? The right side. As you come to it from here. And what does that y value looks like? 0. And what's the limit of f of x as x approaches 1 from the left side? The 1 here, you're coming from this end, from the left side. That's also a 0. There is no limit from this end, there is no limit from that end. The function is not defined there. So for the negative one, the function is continuous from the right side on, not the left side. Continuous from the right side till you get to this point, then it's continuous from which side? The left side. Continuous from the right, continuous from the left. Here's some properties about continuity. Just some rules. Our book is really good about throwing some rules out. Oh, let's look at these. So I'll throw some of these properties of continuity. I'm not a fan of listing rules, but I'll put them there. Just like when we did the limits. Here's what we know. If f and g, we have two functions. I'll go f. I should write f of x and g sub x, but I'm lazy. Are continuous at x equals to c, then the following functions, if they're both continuous at x approaches c or equals to c, then the following functions are also continuous. Are continuous at c. What are the following functions? If you multiply the two of them, if you take f of x times g sub x, they will be continuous at c. Our book might write that, or some math book will write that fg. If you multiply them, the new function, when you get it, is also continuous at that point, as long as both of these are continuous at that point. If you add them or subtract them, doesn't matter which one you do, it's also continuous at c. If you divide them, as long as g is not 0, because you can't divide by 0, is also continuous. If you multiply them by a constant, it's also continuous. Our book writes them. I'm just saying what our book writes them. Our book writes them this way, that way, this way, this way. But that means the same thing. If you multiply either one by a constant, f or g, by a constant, by a scalar, by c, by a number, the new function will also be continuous as at x equals to c. That's really what the properties of continuity. And the last thing in this section, so beside the properties of continuity, the book just throws them there. So, hey, it's nice to know. The function is also continuous. If you multiply these functions, if you add them, subtract them, if you divide them, as long as the bottom is not 0, if you multiply them by a number, still going to be continuous. As I said, I'm not a fan of just listing properties. Maybe that's the engineer part of me there. Math people loves that stuff. Engineers, they go, hey, just show me how to use it. I don't care. Intermediate value theorem. You hear that a lot. I don't know how a lot, but once in a while. Here's what it says, the intermediate value theorem. If f is continuous, on the closed interval, that means including the endpoints, from A to B, and k is any number, between, we'll talk about that in a minute, f of A and f of B. Then there is at least one number we call C, that's between A and B, belongs to that interval between them there, such that f of C is equal to k. And that's the intermediate value theorem. Let's see what that means. Let's pick a function that's continuous from A to B. Let's assume this is A and this is B. I have a function, continuous. I don't care how you graph it. You decide which way you want to graph it. It looks like a two-hump camel. Is this function continuous from A to B? Let's look at it. Continuous in a closed end from A to B, including these points. Yes. Then it's, let me change just a little bit there. I don't like B, it's the same, almost the same height. It could be, it doesn't have to be. But let's go like this. This is f of A, the y value at A, and this is f of B. It says if you pick any number between this value and that value, any number, pick anything that you want. Let's pick this point, like this one. That's my k. Between this value and that value. It says there has to be at least one point. So if you draw a line there, there's at least one point between A and B where the value of the function is equal to k. Well, I see actually in this picture, I see 4 of them. This is 1, this is 2, this is 3, and this is 4. There are 4 values between A and B where the y value at that number is equal to k. Anywhere you slice it, it has to be at least 1 point. When I did this initially, I had A and B the same height. Well, I couldn't do that because it says pick K between, if they're the same height, how do you pick a point between them? So you couldn't pick a point between them. But you can think of any picture that you want to. You can say this is A, this is B. This is f of A, this is f of B. If you pick a point between these two y values, between this and this, we don't care where, anywhere between them, like this, there has to be at least 1 point where f of c will equal to that number, and that's this value. It has to be between A and B. There has to be a number, at least one, which you can see it here, and the value of the function at that point is equal to k. That's what that means. Where we use that, let's say I like the stock market, and I'm watching Apple stock, and I go, you know what? Apple stock has this pattern. Started here. Let's say this is in January. Well, we can't really use a number. Well, we'll go January. And this is, we are in June now. This is the Y value. The Y value in January, what the stock was worth. And this is what the stock is worth in June, money-wise. I could have used numbers here. If you pick any number between these two prices, any value, like if I pick this, let's say in January the price was 93 bucks a share. And in June now, I think the price today dropped. What is the price? I can tell you right now. Is it 95.10? Today Apple didn't do well, dropped a little bit. 95.10. If you pick a number between 93 and 95.10, any number like 93.75, we're saying there has to be at least 1 day between January and June that the stock market hit that number. Has to be at least 1 day. So if you draw a line parallel to that, guess what? There's more than once the stock hit that price. It hit it right there. It hit it on this day. And it hit it on that day. There were 3 days between January and June where the stock market for Apple, the price of Apple shares, hit 93.75 cents. There's no way you're going to find a number between them where it says, oh, there's not a single day that the market hit that price. No, there's a lot of days. At least one, sometimes more than one. Now, if Apple happens to be like going crazy, not dropping, when Apple was doing good, was still doing good, Apple was going like this. It wasn't really dropping. So if you look at last year, you go, this is January of last year. January last year was 2015. And this is June 2015. Not 16. This is the price of Apple in January 2015. And this is the price of Apple in June 2015. This might be $123 a share. This might be last year, let's say 105. You say pick a number between 105 and 23. You go 117, somewhere here. There has to be a day between January and June of 2015 where the Apple shares hit a price of 117. At least one day. And if you looked at Apple in the past few years, that's what their chart looks like. So if you missed it on that day, guess what? You're not seeing it again. You got to buy it tomorrow at 119, 120.
Or this year, 95.
Yeah, or this year, you know? That's because they just order millions of iPhone 6, iPhone 6 Plus for China. Then China says you can't sell them to us because we have a phone very similar to yours, made by a Chinese company. Like, oops. So now they got these iPhone 6 and 6 Plus sitting on the shelves. They paid for making them, and now they're going to be giving them to people free. If you switch to us, we'll give you this phone free soon.
Just gotta wait.
So that's the mean intermediate value theorem there. That's the law.